Okay, hello, this is Vidvathama 2024 12 2002.
Hello, this is Gopal 2023 112 006, and this is a video for a demonstration and explanation of our EW2 Project 2, which is an ECG circuit, a low-cost device with multiple functions.
Go.
Yes, so our ECG circuit consists of four main stages. The first one of them is an instrumentation amplifier. The second one of them is a notch filter. The third one is a low-pass filter, and the fourth one is a high-pass filter. Each of the stages has a particular function. The first part is an instrumentation amplifier. The main function of this is to amplify the biosignals, which is in a very low voltage range, from 0.5 millivolt to 5 millivolt, up to 1,000 times, approximately 1,000 times, to a usable level. In our current implementation, we have a gain of around 800. The next stage is a notch filter. The notch filter cancels out the 50 Hz frequency coming from the AC signal, which is used in India. The next stage after it is a low-pass filter. The low-pass filter is designed to cut off at a frequency of 150 Hz, which is being verified through simulations and also through FRA analysis on our circuit. Further, the last stage is a high-pass filter, which is supposed to block out the DC voltages coming from breathing and muscle movement. The cutoff frequency is set out to be around 0.5 Hz. The particular set of frequency was chosen keeping in mind the typical range of heartbeat values, the beats per minute, and also in order to preserve the particular spikes used for medical detections.
Alright, so this is our instrumentation amplifier part of the circuit. The instrumentation amplifier part of the circuit essentially consists of 3 op amps, and 3 op amps are the UA741, right? It further consists of resistors. The resistors in turn provide the necessary configurations that we require to obtain the particular gain and the particular phase difference that we require. The instrumentation amplifier in total has a gain of 1000, but in our simulations, that is the real life simulations, we obtain it closer to 800 to 850. Now, if we look at the gain plots, we observe that the magnitude value for the gain is roughly around 53.669 decibels, and this is the phase plot. Now, why do we observe this roll-off? The roll-off we see over here is because of the parasitic capacitances. The parasitic capacitances thereby affect the slew rate, and there's a small change in the phase difference from 180 degrees to a total of 167 degrees. The instrumentation amplifier essentially makes sure that there's a phase difference of 180 degrees, and we are seeing that the difference is not very large, from 180 degrees to 167 degrees. Moreover, it's not a point of contention in our case because this happens only at very large frequencies of around 1 kilohertz, and we are operating at very small frequencies closer to a very lower value.
So the next part after the instrumentation amplifier is the notch filter. The basic purpose of the notch filter is to remove the 50 Hz noise coming in from the AC supply voltage in India. The current implementation which we are using has a parallel T structure. It's a second order notch filter, and we have designed it for a quality factor of 8 and a cutoff frequency of around 50 Hz. As we can be seen from this plot, the cutoff frequency in our simulation is around 50.3 Hz, and it has a very good notch shape over here and provides almost zero gain. Since the previous stage before this had a gain of 54, it is showing here as 54, and the notch here drops off to almost 24 decibels. It is actually an infinite notch, but since we are limited by the simulations, it shows somewhere around 24, but you can see the notch very clearly. In our real implementation of the circuit, we had difficulty producing this exact 50 Hz cutoff, so we had to compensate for the errors in resistors and capacitors by tweaking the value a little bit by 1 or 2 ohms above or lower than actual values which you're using in the circuit, and we managed to achieve a cutoff frequency of 49 Hz in our real circuit.
So here we have the active second order low pass filter followed by the active second order high pass filter. What is the reason for using of these circuits? Because we have to specify a particular bandwidth within which we're supposed to perform the ECG analysis, and we're supposed to negate all the other noises which come before the 0.5 Hz and the 150 Hz which we are ideally trying to achieve. Now, this second order active low pass filter essentially consists of a frequency range wherein we are trying to attenuate all the frequencies beyond 150 Hertz. How do we obtain this particular frequency value and how do we obtain these resistor values, RNC values? We essentially use the formula 1 divided by 2 pi RC. This will be explained in detail with derivations in the report. Then we have the active second order high pass filter. The high pass filter has a cutoff frequency of 0.5 Hertz, ideally DC, because we want to eliminate all the DC noises in this particular case. Alright, so this is our video. Essentially what happens is that this is our entire circuit. The circuit diagram has been given in the report where we'll explain what each component of the circuit is and what function it essentially performs in the entire circuit. This is our patient, right? Here, essentially what we do is that we connect the ECG leads, right? One is put right over here and the other is put right over here. We provide a grounding condition right there, which in turn will give us the ECG outputs that we require. This can be seen in the wave output. And this is our ECG. When our patient tenses his posture or his muscles, there is a change in the ECG. Please tense it. As you can see, there's a change and there's an increment in the amount of noise present. Relax. As we can see that when the patient relaxes his posture, we get a more accurate reading of the ECG. Thank you. Alright, so this is our video. Essentially what happens is that this is our entire circuit. The circuit diagram has been given in the report where we'll explain what each component of the circuit is and what function it essentially performs in the entire circuit. This is our patient, right? Here, essentially what we do is that we connect the ECG leads, right? One is put right over here and the other is put right over here. We provide a grounding condition right there, which in turn will give us the ECG outputs that we require. This can be seen in the wave output. And this is our ECG. When our patient tenses his posture or his muscles, there is a change in the ECG. Please tense it. As you can see, there's a change and there's an increment in the amount of noise present. Relax. As we can see that when the patient relaxes his posture, we get a more accurate reading of the ECG. Thank you.